Okay, so we're starting the portion on fretting. So fretting actually is, you can, you might have also heard that we've had an outage in Darlington. Unit 3 actually was last July. We had a forced outage because of the fretting issue. It's just just a tube, L81. So fretting can actually have dire economic consequences. Safety-wise, it's insignificant. Doesn't have any safety consequences, but the financial impact can be huge. So really what fretting is a corrosion accelerated by abrasion of, at the surface of the material, and damage is induced under some sort of load. Of course, there is the load. It's actually not just fretting like it's like things are touching. There's actually load that is forcing the removal, continuous removal, shaving of material at the fret location. And the protective film, of course, so from one side there are two aspects. So if we have a protective film, like if we have carbon stainless steel, we have a protective film, that gets filed, literally, or shaved. Or if the load is huge, and we have the load that's really causing the fretting, and items are fretting against each other, then actually it doesn't matter the 50 micron, or 100 micron passive layer. It's actually getting shaved. The material are getting shaved at a much. It's like being machined. So the mechanism is mechanical, chemical, and electrochemical. Of course, this is. That's the observed. I'd like to get through this to get to the pictures, but before that, we'll just see the steam generators. So flow conditions, tube dimensions, the tube at the supports, actually this various support positioning, the AVP supports at the vents. Prevention of fretting is through design, not material selection, because you can have the best material, but once you, you're really grinding it against something, then it doesn't matter. So it's really the design. And I want to get to this. This is the boiler, and actually, you look at it. The boilers are this, like our boilers. They've been designed. The Pickering boilers, of course, Pickering A. They've been designed in the '60s because they were installed. The first units start to get operational in '72. So they were designed in the '60s. The B side, they were designed in the '70s. And so on and so forth. There's a little lag because it takes years to manufacture a boiler. And the design is it depends. The design takes from the state of the art of that particular time. So in the '60s, they thought, and they had good designs actually, it's a good design. But sometimes we do find these issues as we go further or as we progress. You'll find, for example, that as you can see here, there's a lot of the bundles. The bundles are actually, this is huge. This is just a single tube or a single line of tubes. If you actually look at it, you can see this is like spaghetti. This is a noodle ball. It's a lot. And these are the supports. So the way these supports are placed and the spacers, because you don't want the tubes themselves to hit each other and to vibrate and keep banging each other, but you want so you put spacers, but sometimes the spacers can become also the problem. It can actually cause they will be the location where you actually fret. And we're talking about the boiler, there are thousands of tubes, 4,000 tubes. A normal boiler, an average boiler at the periphery, there are 4,000 tubes, like 2,000 something tubes going one direction, and then they're going down, so your tube sheet actually has 4,000 holes, possibly more. So once the tube bundle is actually installed, and all the best effort has been taken to actually maintain your bundle from the vibration and from sweating, you still observe something, because we do the testing and we put bob and plug tubes, and we actually push them all the way up into the boilers, and then we get them down from the other side. And as it's going, it's actually measuring the thickness. So it will tell you if there's wear, because it's measuring the thickness. So it will tell you if there is wear, or if there's, especially if you can map this to the location of a spacer or a support plate on the outside. So this is, well, clear, of course, that's the feeders, and these are so actually this is the feeder. This is the PhD feeder, and I know Claire has a lot of experience there. She's the major component lifecycle management, so they do a lot of the inspection campaigns. And look at this, really, this is your feeder pipe. This is like, this slither of metal is what's standing between you and the fuel. Literally, once something goes in there, it will go into the next thing it will be in touch with the fuel. But not directly, of course, it has to go through the flow path, but I mean there's no physical barrier. It's going straight to the fuel. These are the resistance temperature detectors, so we use a lot of these, especially in Darlington. Like Darlington has thousands. So how many are there,
I think maybe hundreds, but not thousands.
I thought it was hundreds, okay. Maybe the contact points are 4,000.
Maybe
The contact
not-
points.
not everything.
Yeah, the contact points across, so each line has several contact points. So I think University of Waterloo back in the day, they did a study. So it was like 4,700, contact points. No, but actually there are hundreds of them, especially in Darlington. And these are resistance temperature detectors, and they go around and they carry, and it's not just that, it's also tubes that will carry will go to where the sensors and detectors and gauges for pressure, so the operations are able to get an idea about what's happening, and that's how they control the reactor. So there are hundreds of these going around. As you can see, this is really a very small pipe, or a very small, and look at how much actually it has eroded, or it's fretting, and that's a feeder. I don't care about this one to break, because it doesn't have, it has the element.
It's the wire in it.
Wire.
So there's no water.
There's no water.
No water.
So-
So if this is what you see, just the gut tube. So the temperature detector is a wire inside this gut tube.
Yes.
So even the gut tube get frets, so wall is doesn't matter.
But the feeder, of course,
Feeder.
we don't want the loca. What happens here is it's a loss of coolant. Maybe small loca, but loca. So I mean, even with this one, if I lose this one, I'm only losing signal. But if I lose this one, I'm losing coolant. So, that's where it's, but that's fretting, and I don't think we have a picture of the reactor and how it, but of course all of us have seen it, and possibly even some of us have gotten that close inside. What you have there is there's a very big potential for fretting, because of the way all the tubes and all the feeders are, and the pipe supports. So you can actually have fretting between the hangers and the feeders, the supports and the instrument lines. It's it just doesn't stop. Yes, sir.
So essentially, or what we're saying here is that RTD guide impacted the side of that feeder tube, and then it corroded from the inside out because of that?
No, not from the inside out. From the outside. It's
From the
outside.
outside in?
Yeah.
Then you get pitted against it, so probably like in between the stick to it, or touching it.
Yeah.
So like constantly hitting it?
Yeah, it's the reactor is vibrating always because of the flow. So there is the flow, and it's always vibrating. So as it's vibrating, there's a load. These actually lines, and still, even though it doesn't have water, doesn't have the surface fluid, they're pretty strong. I mean, it's like a metal. It's like maybe a couple of millimeters or a millimeter thick. So once they get loaded, as the reactor expands, because every outage is a maintenance campaign. You have to pull your fuel, the end, you know, you're doing the cigaring and slaring. So actually what's happening is you do introduce this movement. You do introduce this movement. So what happens is sometimes you can actually get, and it's very complicated to find, to see. They do their best effort to try to look and try to identify if there's any like interferences, but sometimes these interferences don't show up unless you actually restart the reactor. And it heats up, then these lines start to peg against each other with load. And as the, so this here is in, obviously they've taken the picture, so this is during outage. And it's not leaking, fortunately. That was, and so probably this is during VBO. Probably. It's in 2010, or maybe in an outage after VBO.
2009 probably.
This was 2000, it says the SCR is,
I think the Darlington VBO was 2011.
no, but this is Pickering. Pickering was 2010.
Oh, then it was then.
Yeah. Probably this one was, probably they found, or maybe in an outage after VBO. Yeah, we don't know. I mean, it's not really significant. But what I'm saying is that it has to be taken, this picture has to be taken when the unit is cold. So that's why you see they disengaged. Like, as it's hot, they are maybe pegging against each other. And this fretting is happening and this loss of material. But as the reactor cools down, for us to get in there and look, it's kind of like they disengage, as you can see here, yeah, you can tell.
This disengaged is because of the corrective action has been performed.
Yes.
You see those wires? This is
The wires
yeah.
pulled it.
Yes.
Are
Yes.
these temporary or like
The-
permanent or for permanent separation wires?
This is considered permanent corrective action.
That's the permanent, oh, okay.
Yeah, it's not a.
Or chafing shields. Or sometimes you put chafing shields.
Yeah.
They just put a sheet of stainless just wrapped around the pipe.
So would they go in and take a piece out of the feeder?
For this one, I don't know how they repaired it.
No, this is within the allowable, so the did assessment is still acceptable.
Yes, there you go.
At this section,
So-
there's no tool,
Was it far right enough?
no technology to replace it.
Oh.
So this little scallop is within our allowable, so they left it. And actually, once they removed it like this is corrective action. Once they removed it like this, it's not going to stop. It's going to stop. It's not going to happen. Yes, Amar?
Question, so you did mention about the cigar tool, right?
Yeah.
So when they enter the cigar tool to the inside, are they looking for this as well, or are they just looking for cracks?
Clear.
These are different programs. So cigar tools is for full channels, and this is interim line, the feeder, those threads, contacts is managed by feeders. So it doesn't matter if cigar is going on or not. Feeder will scope the inspection for this kind of issues at the outage.
Okay. Cigars only.
So there's many activities. There's cigar, there's SLAR. There are also the activities for the for your the spacers, the feeder spacers. So there are all sorts of activities. Whatever you do, because there are a lot of feeders. It's like really 360 in Pickering, 480 in Darlington. Whatever you do, any kind of activity, if you kind of move something, you're making it get closer to something else. When you start, there is the possibility that as expansions happen, so we're very lucky actually that this is within allowable. We're extremely lucky. And because otherwise, so they said there's nothing there because why didn't they try to rebuild, like fix by welding?
No, I don't think that they fix it by welding.
No, why not?
Well, welding is you're going to introduce more stress. You are going to need to do a lot more analysis.
Yeah.
But
Yeah, and it's very congested, so maybe the welder said, listen, we're not gonna go there and yeah, yes. Yeah, it's not possible. If it's not possible, it's not possible. If it is not possible, the welder, you have to listen to the welders, like, you know.
No, I think the feeder corrective action, there's no re-weld.
Yes.
We first we do the disposition, and also we protect it. The next
Yes.
step is replace it. So there's no like a re-weld.
But we're not doing replacement, are we? This was not replaced for
If
sure.
it is below the allowable, the acceptable limit, we have to replace.
Yeah.
That's the only option right now. But if it is very hard to replace at this location, we may like seek other options, maybe welding.
Ice plug? Ice plug or something? Would you use an ice plug just to?
No, the ice plug
you
is
can't.
to isolate this channel from the whole circuit.
Yeah, there are, yeah. It gets pretty complicated, like, you're not complicated, it gets pretty interesting because you have to, like, you know, see a little fret and it could open the door for what do we do? Do we do this? No, we can't. Well, you know, design considerations, operational considerations, what our machines are able to do, what they're not able to do. So there are all sorts of, like, you know, considerations like this. So this is, now, oh, that one. Microbiologically influenced corrosion. Actually, so I'll show you an example. We have an example, and it's actually been recurring all the time because it's like squirrels or raccoons. You can't get rid of bacteria. They just once they strike a system, it gets stuck in the system. That's it. You have to live with them. And he said, I'm going to show you pictures, and they're pretty funny, actually, if you want to look at it from that perspective. So it's corrosion that's influenced by the presence and activities of microorganisms and their metabolisms. So actually, just bottom line is these bacteria, the metabolism, their anabolic metabolism is actually sulfuric acid. So they form a colony. I'm going to show you the colony. They form a colony, and right in the middle of the colony, all their, you know, the metabolism, literally their poop is sulfuric acid. So it pools right in the middle of that colony, and it is drilling. It's drilling within really days, especially if you have stainless steel tanks, like in the radiological waste water tanks. They're all stainless steel, so I'm going to show you the pictures. It's all holes. Well, not too many holes. But once you have the colonies there, it's impossible. It's possible to get rid of them. And it's because of the metabolism, the activity and the metabolism. So microorganisms are present almost everywhere: soil, fresh water, seawater, air. Now, MIC, microbiologically influenced corrosion. So it affects the cooling towers, heat exchangers, storage tanks, fire sprinkler systems. Now, the microbes colonize surfaces and produce a biofilm. So encourages sediment, particle attachment, excretes sticky polysaccharides. So that's, of course, reduces the supply of oxygen to the metal surface and creates anaerobic conditions. I just want to see, I'm just weighing it in my mind. Okay. So the biofilm formation, I'm going to show you one. This is just a diagram. I'm going to show you the actual colony in real life. So you can see here, the bulk fluid is here. First of all, you get you know, the microbes. Then they form a colony, and then the colony grows. And the bulk fluid is going here. So this is the growth. So attachment, colonization, and growth, and that's the surface. And all the sewer of the colony is actually what affects the meta, and it does affect it. It affects it in a bad way. Prevention of MIC is to prevent the growth of biofilms, flushing the system, mechanical cleaning with sponges and pipe within the piping. So you can actually, it's called pegging. So you use pegs to actually, if you have a pipeline, so these are pegs. Oxidizing biocides, and non-oxidizing biocides, and selection of material. So I'm going to show you some example here, actually for this one. Well, so these are the culprits. This is bacterial colony. This is bacterial colony. And this is inside the radiological wastewater tanks, the very bottom level in Pickering. And apparently, our license, I mean, these pressure vessels are really open to the atmosphere. It's not really, it collects all the effluents from the lab, from the floor. So it's not really, not very highly radiological. It is active, and but it's not really high pressure. It's not like a pressurized pressure vessel. It's not. It's just a tank where the lab washing of for example your lab equipment, something that goes there, maybe some floor drains. And so this is treatment. There is a system of, I think, 4 or 3 tanks, or 4 tanks, and 2 or 3 ionic exchangers. So really the ionic, they're all the same design, they're all the same size, except some are the tanks, which I think there's some additives or something gets put there. And the ion exchangers are just the tanks with large chunks of lime. So after it gets treated and everything, and the lime just adds some hardness to the water, so that before it's discharged to the environment, it's like it's been treated and you add some hardness, so it doesn't affect the environment. So they're just large chunks. So it's not really a pressure vessel, but it's licensed as a pressure vessel. And apparently our license as a plant is related, or is actually attached to it. So that's why. So these are, and they're just attaching themselves on the vessel from inside. So when you look at it here, actually these are some examples. So that's the vessel. This is from outside, what you saw from inside. This is here. And it's actually, it's just, and all these, incidentally, we used stainless steel. We determined the material would be stainless steel. And I'm not us, it's like, OPG and whatever vendor we had. And with that stainless steel tanks, you can see here, what we got is all sorts of pinholes. So they're not even structural, like you don't have to repair them for structural integrity. They're just pinholes, less than a millimeter. Because the colony on the other side, they're just producing sulfuric acid. And sulfuric acid and stainless, it's. So this is what we're getting here. And every single portion in that system was actually, either from the bottom, the tank discharged from the bottom, the side. You can see this tank here. You can see this water. This is stainless steel. So where is this coming from? It's the rust from all the water. It's the corrosion products that's in the water. It's just resting there. It's actually just showing itself there. Because the water has the rust and the iron from the system. So here, other. So these are the tanks from the bottom. These are the discharge lines here. You can see that's a pinhole, that's a pinhole. These are other pinholes. These are other pinholes. West, east, it's everywhere. It's all across. It's infested. It's actually infestation. And we tried to clean this, or no, we didn't try to clean it actually, we tried to abate it, Well, first of all, our repair strategy, the design that we're working with, said, fine, we're gonna weld. So we're gonna place welds all around in order to plug these holes, these tiny holes, so we don't have leakage. Plus, we're gonna add extra layers of weld on these lines here. So this is the vessel. We said, fine, we're gonna put more welds here. So whatever weld is there, we are going to actually deposit more welds. And they use that in order to abate so that the microbial colony on the back gets killed. So these microbial colonies get killed from the heat. I'll tell you that was back in 2014, December 2014. So since then, so 2014, 2016, 2017, 2018, 2019, we have been going to repair. There are all those pinholes. They say, we did the inspection, the pinholes. So we go, but we're not doing the abatement because obviously it's not really, so actually when you look, I'm saying that part as a welding engineer, so that's what we're doing. So flushing the system, so that's, yeah, abatement or how to prevent it, or not prevent it, how to prevent it or prevent return of this, the MIC, or, so it's flushing the system, mechanical cleaning with sponges. I mean, for that one, we could have saved ourselves a lot of effort if they just opened the hatch and somebody with a sponge actually removed those colonies, but yeah, not necessarily accessibility. People have to wear rubber because it's a radiological area. So maybe the use of oxidizing biocides, but of course our environmental folks don't want it to be that close to the lake because we're not going to be able to remove it. So how are we going to remove it? We can't. So it's going to stay there. So this is in general. So this is like prevention of analysis. So this is in general. But the reality is, we look at it and say, where are we going to catch the discharge to clean it further? We don't have to, so we can't use oxidizing or non-oxidizing biocides. And selection of material, of course. That system, when we looked at it, it actually had a cycle of ultraviolet tank to actually kill the microbes. But somehow
doesn't work.
it doesn't work. Okay, that's why it wasn't installed. It was not installed actually.
And the MIC normally happens when there is a low flow or no flow.
Exactly. This is low, no flow. Yes.
And some temperature.
Yes.
So that's why you are saying that flushing the system. But basically, to arrest the MIC, you should have some flow.
Yes.
And,
these tanks are actually, as I said, they have these large chunks of lime, and they're just sitting there stagnant. Yeah. So we'll keep plugging those holes.
active liquid waste system.
Active liquid waste system. Yeah. Yeah. Yes.
I thought we added some chlorine to the water as well.
Where?
I thought we added some chlorine as well. to the
You
water.
can't. This is stainless steel. You add chloride or chlorine, your system's your tanks are gone. Then we're dealing with cracking.
Cracking.